Now, let's think about the charge current at a p-n junction. There are two mechanisms of the charge transfer in the p-n junctions. So let's study this. So first up, I would like you to show the reminder the p-n junction case. So there's some depletion region. This. And in the N-type side and the P-type side, and you have a common Fermi energy. And as we called in this, the Fermi energy, the band is shifted. Band shifting region is called the depletion region, where the positive charge and the negative charge are accumulated to control the charge compensation. So this positive coming from the donor side, donor gives the electron, and then this negative charge is acceptor level accept the electrons. So I would like to stress that these positive and the negatives are not mobile, right? Mobile, because these are the lattice of the donor and acceptors, which cannot be moved along. So these are the static charge. And on the other hand, in the N-type side, here outside the depletion region, you have so electron excited and E. So this can move around in the N-type, and then in the P state, so you have an electron excited and then holes generated. So holes can be moved around in the P-type side, right? And there are two, as I mentioned, there are two types of the charge transfer process. One is diffusion, and the other is called a drift. So what it means, okay? The first process of the diffusion, you can see that in the N-type side, there are more electrons, right? More electrons. And here, more hole. So due to the concentration gradient of electrons, so more electrons on the N side, but there are less electrons on the P side. That's why due to the diffusion, it moves from the N to P side. On the other hand, from the P type to N, the holes can move due to the concentration gradient. You can imagine that very dense, high dense chemicals can gradually become lower concentration due to diffusion. So that's the same principle. So high concentration part diffuse out toward make the concentration homogeneous. That's the diffusion process. And on the other hand, drift process, there's a in this depletion region, very rare case, but by using the thermal energy, it could be possible that electrons are excited and holes are generated, and electrons can move towards the lower energy, and holes are moving towards the higher energy for electrons. It means that holes are for holes that the higher energy level is actually lower energy, more stable. So that's why these two are moving around. So key point for this is drift process. So this is drift process, and then this one is diffusion process. Okay. So think about what will happen if the bias is applied. Bias meaning the voltage applied. There's a definition of the direction for the bias voltage, and here's the thing. So originally it is something like this, the PN junction, original PN junction. So when the positive bias is applied, these are shifted. So by increasing. Okay, and then p-type side became lower, and then this one a bit lower, this one lower. So it must be connected and like this. So what happens here, by applying the positive bias, for the diffusion process, this barrier, originally there's a barrier for here, but the barrier is lower. For holes too, the barriers becomes lower. That's why diffusion process increases. And this diffusion process is actually proportional to the, like this, E V over kVt. So by applying the voltage, the current increase was V, right? So exponentially by V. So that's a positive bias case. So what happens, and as a negative bias case, So thinking about the original case. So compared from this, so opposite way, you can move the here. Like this. So by applying the negative bias, the diffusion is more difficult because the for electrons and for holes in the N-type region and the P-type region, the barrier is become much higher. So it's very difficult to move around. On the other hand, in the depletion region, the electron hole and electron is generated, and this hole can move toward the P-type and N-type region. There's no effect by applying the negative bias, right? So this process actually does not depend on the voltage. So always you could only see the drift or current and there's a negative bias. Okay. So in summary, in total, you could obtain the total current like this: J of 0, exponential, this KEB over KBT minus 1, which is not 1 actually, it's equal to G0. So this component, it corresponds to diffusion, and this corresponds to drift current. Okay, so you could summarize the graph like this by applying the voltage. You could see exponentially increasing for the current, positive current. Okay. On the other hand, for the negative potential, negative bias, there's a constant current, but opposite the sign of the current you could find. So that's why you have a minus here. So you could remind you that if the current is electron is going into the p side, right? So drift current. So electron is going to p side, that means positive current. And the opposite direction case, you have a negative current.